A very interesting consequence of mixing the universal law of gravity with Newton's third law is that the force of gravity, that the bigger planet, like for example, let's take like a big planet and a satellite, like a moon. When I say satellite, I mean like a natural satellite, like a moon, like an orbiting moon or something. So yeah, so the force of gravity that is applied on the moon towards the earth is the same that the moon applies on the earth towards itself, towards the moon. Now, the interesting thing about this is where we get to, I don't know why, I just thought of this and I'm like, it's just a cool thing to talk about. Tidal locking.
We
Tidal
already
locking.
talked about this.
Oh, did we already spoke about it?
Astronomy, yeah.
Oh, I think we did,
talked
right?
about
I mean,
this.
let me just touch on it for
go
those that
ahead,
might
go
have
ahead.
forgotten.
Yeah.
Tidal locking is a really interesting phenomenon that you see in various planetary systems with a planet and its satellite, again, natural satellite, where basically because the planet is more massive, obviously, than its satellite, it is tugging, or the force of gravity that it is applying on the satellite, even though the magnitudes are the same, relative to the size, relative to both the masses, it's kind of more on the smaller satellite. You know what I mean? Like pushing the Earth with 1 Newton is going to be harder than pushing the moon with 1 Newton, even though 1 Newton is nothing. Just that analogy is what I'm trying to get through. Like, because it's a smaller object, it's easier to push around. So because the satellite is naturally a smaller object than the planet it's orbiting, it gets pulled technically a little bit more than it pulls the planet, even though they're
Well,
pulling the same. It's just the effect on
I
that
think
planet.
this is just easily explainable
Yeah.
by what we were saying earlier, how the inertial term here is the mass, and so it's the Earth opposes that pull from the moon more than the moon opposes the pull
Well
from
put,
the Earth, because
put.
the moon has a smaller inertial term. Even though third law, Newton's third law, they both feel an equal force
Exactly.
pulling towards each other. It's just the moon, it appears, I mean, from our perspective, it doesn't even look like anything's changing except for the tides, which were only connected to the effects of the moon relatively not that long ago.
So that's definitely, the inertial term is a better way to put it, to think about what I was saying. I know I was kind of fumbling in the end, but that understanding that will then lead to the fact that, hey, because this smaller object is feeling, I'm going to say feeling a greater force, even though you guys now know that's not true, but feeling a greater force, not actually greater force. So now that the smaller guy is feeling that greater force, what's happening is there's one side of that planet that continuously gets tugged towards the bigger guy, right? Because as it's orbiting, there's going to be one side, let's say the satellite's also rotating in its own axis. There's going to be one side of that satellite that continuously gets pulled towards the planet. And basically what this causes is a slight bulge in the satellite. Also, because remember the forces are the same, it also causes a slight bulge in the planet. So in the mother planet, it also causes a slight bulge. So for example, a commonly known fact is the Earth is actually not spherical, right? It's I think like some 40 or 50 kilometers wider at the equator than at the poles, right? Because it's got slightly a bulge. But now the moon, having such less mass than the Earth, is affected a lot more. So the bulge is so prominent that it basically faces the Earth forever and basically cannot rotate anymore, because that one side is so much closer to the mother planet. And that's the idea behind tidal locking, because of the fact, because of the mixture between the universal law of gravitation and the fact that these forces are equal. Because these forces are equal, this is possible. Right.
It doesn't face the Earth because one side, I mean, if you go deep into it, I guess it is because one side is being pulled more than the other.
Yeah.
But it's actually because the Earth is rotating, right? The bulge from the Earth is actually, it causes a torque, because when the moon was rotating, the torque that the bulge we say bulge a lot in this conversation here.
We have to. We have to.
But okay, so the bulge of the Earth, what it does is it creates a torque on the moon that slows the rotation of the moon down, and then over time, the moon slows down, and then eventually stops with respect to the Earth, and then that's why we only see one side of it.
And interestingly enough, right now, the moon is moving away from us at a rate of about 2 to 4 inches per year.
And actually, the reason for that, is because once again, the good old bulge of the Earth is actually pulling on the moon, slowing down its orbit. The moon is actually moving slower and slower around the Earth every year by a small amount, but the reason why it's moving away from the Earth is because of the conservation of angular momentum, which has to do with which has to do with the velocity and like distance from the point of rotation and all that stuff.
Mm-hmm.
The actual equation is MVR, right? Mass, velocity, radius. If it's like a perfectly circular.
Yeah, I forgot the formula.
That's right. I'm pretty sure that's definitely
so.
right.
Mm-hmm.
But so essentially, what I'm trying to say here is that the angular momentum is conserved, and so if the Earth is slowing down the moon, the velocity is decreasing, then something has to compensate for that. And in this case, the mass is not changing, and so the radius from the moon to the Earth has to increase to compensate for that decrease in velocity.
How
and
is
so
the moon
so,
wait, isn't it?
Moves away.
Isn't it the other way around? Because the moon is actually pulling on the Earth now more than because the moon is already tidally locked with the Earth. Interestingly enough, and everyone's going to love this, Earth's rotation is actually slowing down. So one day is getting longer and longer every year. Now, obviously by a microscopic amount.
Wait, is that?
That's what I'm saying. I think you said it the opposite.
I think that's right.
I think you said it the opposite way. So basically the moon is actually tugging on the Earth. That's causing the Earth to slow in its rotation. When the Earth is slowing in its rotation, the energy has to go somewhere. So that basically translates into the moon gaining energy and moving away from the Earth. And that's is simply because they are both not tidally locked to each other, but instead the moon is only tidally locked to the Earth and not the other way around. A common example, Pluto and Chiron, one of its satellites, are tidally locked to each other. So basically, if you look at this planetary system, they're always facing each other, which is like a really cool sight to see. And yeah, so that's basically why the moon is moving away, which is, I think, a really cool topic that you brought up.